exercise 26. Let's look at this exercise 8.1.5 in Weber. So suppose we have R for I maps from AI to CI. So this category at this moment we don't put any restriction. A family morphism. Let's see, show that first question. If product exists, show that there is a unique map between the products such that it commutes with these product projections pi I. Secondly, show that it preserves monicness, monomorphism. So the first part is easy, so let's say just by universal property or exercise 8.1.4 if you want. So this is just basically we have the home set between any object in C, and product of CI is bijective to the home set of is morphic to the product of the home set is in the category of sets. The product is in the category of sets. Okay, any object CI. So in particular here, what we know is that we got this family morphism from AI to CI. In particular, this is telling you that you have a map. So let's take careful. Product of CI, okay, and product of AI, because it's pi I. Let's also call it pi I. About the universal property of product of CI, there exists a unique map. Let's call this alpha, making the diagram commutes for any I actually. Okay. Let's construct this map alpha such that alpha followed by pi I equals pi I followed by alpha I, any I. This is the second part of the exercise. The first part. The second part is showing that it proves the monicness. Suppose we have the monicness of alpha I implies alpha is monic. That's the question. This is the question part. Okay, what we have proved is such that this is the question part, such that this is this holds. So now for this second part of the question, we check by definition of monicness. So suppose you got two. So the monicness means you could cancel from left hand side. So if we have alpha composed with F equals alpha composed with G, this means that there exists some F and G starting from some for any object and then FG such that alpha composed of F equals alpha composed G. The question is, does F equals G? So obviously we would first say that this implies alpha I pi I f equals alpha I pi I of g, and then the fact that alpha I homomorphism implies monic, imply that pi I compose f equals pi I compose g. And it would be very nice if we know pi I are epimorphism, then this one be done. But it is true in general, this is not true. Actually, you can find counterexamples. But all the counterexamples, you will see that they are very extreme situations. So just one assumption would help us to got this. I'm not sure if we could move this for this exercise, but let's just suppose this is the case. What is the case? Let's suppose the home set for any AIAJ is not empty. Okay, which is not really necessary, but this is the case. For example, if zero object exists, then the home set would be there would be at least the zero homomorphism in each home set. And for example, if this is a linear or pre-additive, then any home set is within group at least will have the zero. So some assumption like this. Not sure we could remove this to prove this. If you think so, you could put down a comment. Let me see. Okay, thank you. So under this assumption, so let's see how it works. I'm going to prove pi I is epimorphism. So the way we work is that you just start with arbitrary AI, and to construct a map to the product of AI actually conversion. Suppose you got the product of AI already exists. I'm going to construct another map by defining this to be the identity of the AI, and on any AJ different from I, I'm going to say that this is whatever some morphism in this home set. Okay, for example, if there is a zero object, you could put this the zero morphism, but it's not necessarily put the zero morphism there. And then by the universal property, there exists a unique morphism. Let's call this rho I, and then this rho I satisfies rho I obviously I put the wrong direction. Okay, what I should do is, remember we say the universal property is always you put the testing object further than your universal object. This is my universal object. Okay, so I put my test object further. I'm going to do it like this, and this is identity. This is some morphism, for example, the zero. And then by the universal property product of AI, there exists a new morphism, let's call it rho I, such that, so first apply rho I, then apply pi I, computation gives identity. That's all what I need, because if you got this, I could show pi I is epimorphism. How do I show that? So how do you show pi I is epimorphism? Again, by universal property, what you have to show is that you could cancel it from right hand side, right? Which means that compose with whatever b and fg. Suppose have compose pi I equals j compose pi I, and then by this condition we got, just apply here, which means apply composition with rho I. What you got? You got exactly f equals j, and that shows pi I is epimorphism, and so we prove f equals g, preserves monicness. This finishes the first part of the exercise, and actually exactly the duality gives you the second part of the exercise.